from what we discussed last, but similar to what we did. Now, if I can recall, last class, we created some relationship. We created a relationship between pressure, volume, temperature. We also talk about the PV is equals to nRT. More important, we're able to solve for the molecular mass of a gas. To solve for the molecular mass of a gas. And we're able to achieve something in the last class under CHMO. Today, we'll be treating more of like the other part of gas. So I want everybody to pay attention. Very, very important part of gas, because this is a part that I believe that you should always see in the exam. And I noticed from the last previous exam, that is JUPEB exam for 2021, there are a lot of questions from this section. So please, I will advise everybody to not joke with this class today. Now, on my slide, we start again with probably ask questions, so we can, one way or the other, understand how questions comes out and how we can relate to questions. Now, the first question they ask us that which gas closely approaches ideal behavior at room temperature and pressure? Good question. Ideal gas. We have what they call ideal gas, and we have what they call real gas. Real gas. Now, in ideal gas, we believe that at ideal gas exists at high temperature and low pressure. But for real gas, we say that ideal gas is being deviated from when we have low temperature and high pressure. When this happens, we say, oh, this is a real gas. This is a real gas. Now, guys, in this question here, we're asked, we're now relating it to the nature of gas. Now, we need to know that out of the nature of gas, this gas, now can we pick which of the gas there we behave more ideally? Now, when we know the gas that will behave more ideally, they will always have what they call low molecular weight. Low molecular weight. When we say a gas that have low molecular weight, we say that it is the ideal gas region. But high molecular weight, we always have the fact that it tends to deviate to what? Deviate from ideality. That is, it goes to real gas. So from the option there, we have helium, carbon dioxide, ammonia, oxygen. He said, which gas closely approaches ideal behavior? So the only one that can approach ideal behavior is it to be a gas that has what we call low molecular weight. And from the question, they can easily pick it. And that is helium. Why is it helium? Because helium has a lower molecular weight. Carbon dioxide is 44, CO2, ammonia is 17, oxygen is 32. Helium is in the range of 4. So we look at the fact that helium has low molecular weight, and therefore we need to know that it will approach the ideal behavior. Number 2, the division of gases from ideal behavior is due to one of the following reasons. We are still under this, so please pay attention. Now, the division of gas from ideal behavior is due to one of the following reasons. Now, we know that, let's recall what we learned in assumptions. We learned that gases do not exert either attractive or repulsive forces. So when a gas is exerting attractive or repulsive forces, then we can easily say that it is deviating from ideality. I take that again. That under assumptions, we said that gases do not exert either attractive or repulsive force. So when a gas is exerting attractive or repulsive force, we can conclude that such gas is deviating. Deviating from ideality. Please note that. So when we are saying attractive or repulsive force between gases, it's deviating from ideality. So you look at the options there. So the area of gases from ideal behavior is one of the following reasons. 1, no force of attraction between the molecules of gas. That is correct. No force of attraction between. So we know when we see no force of attraction, that is present in ideal gas, but we never deviate from it. So that is out of the option. Negligible volume of gas molecules. Yes, we said earlier on that it has what we call negligible volume under assumptions. So it will not deviate from ideality at that condition. No. Sufficient attractive forces among the molecule. That is correct. So there's the presence of attractive force among the molecule. We can see that will what deviate from ideality. The option D is even wrong because that is more of like ideal gas. High temperature, no pressure. No. So the best option is option C. Why? Because there's presence of attractive force in the gas molecule. So that answers that question. And I had to quickly pick out, when I was going to the question, I had to pick out one of the questions I gave for attempts so we can practice it together. One of the for attempts so we can quickly practice it together and get the gist about everything there. Now, we need to know that normally, we have, I was looking for a question like that. I think I have been seeing such questions, but let me just discuss about it. Now, we have ways of extracting gas or ways of displacing gas. We have what they call ways of the displacement of gases is in two forms. Displacement of gases, please pay attention. Displacement of gases. Displacement of gases. Because it just came to my head now. So it's in two parts. Number one, we have what they call downward delivery. Downward delivery. Downward delivery. And we have what they call upward delivery. Please, it is no different from what you know. Downward, upward is the same English, but we need to understand something here. Let's consider something here. Let's consider a gas chamber. And this gas chamber, please, there are two gases involved. Let me just put X to show that there are two gases involved. Now, for instance, let's say for instance, these two gases involved is let's say I have CH4 gas, and that is methane gas, and hydrogen gas. We know methane gas is what? CH4. Hydrogen gas is H2. This is like you saying 2, this is like you saying 16 grams per mole. 16 grams per mole. Now, 16 and 2 grams per mole. And what you can see here, you can easily say that CH4 has a higher molecular weight than hydrogen gas. Yes, we can see that. We can see that. Now, what does all delivery now come into play here now? If I want to remove hydrogen gas here, for example, I have to do what they call upward. I can either remove H2 through downward delivery or what? Downward delivery or upward delivery or downward displacement. What do I mean upward delivery? In the sense that CH4 is denser than hydrogen gas. Higher molecular weight is denser than it. So we believe that since it's denser than it, it will settle down in the gas chamber. It settles down. It settles down. So if it settles down, that means you can easily remove hydrogen gas. That is what they call upward this thing. You have displaced it, go away. So it's going to stay up. So it is being displaced upward. So that is what they call upward displacement. But that is what they call upward displacement. Sorry. Upward displacement. And if it's upward, if hydrogen gas is displaced upwardly, you can easily say that this CH4 gas can be what? Delivered what? Downward. Why? Because it is what? It is denser than hydrogen gas. So those are things that you must also pay attention to, because you can also see questions like that too. Now, the reason I bring out something like this because there's a question like that says a gas is placed over water. Now, if a gas is placed over water, please pay attention. If a gas is placed over water, you must notice one thing there. That for you to get that, for you to get the now, he said a gas is collected over water at the temperature where the vapor pressure of water is known to be. The vapor pressure of water is 25 millimeter mercury. It says total pressure recorded or in the container is 7 pressure in the container, pressure of gas pressure of the container is what? 775 millimeter mercury. What is the pressure of the dry gas? So pressure of dry gas. When you get the pressure of dry gas, this law is what they call Dalton's law of partial pressure. Dalton's law of partial pressure. We know that pressure of dry gas plus pressure of water will be equals to the pressure millimeter mercury. 750 millimeter mercury. So we can that as this is the pressure of the dry gas. You can see that in option D. That's an option D. Answer. Let's go on. They said, which of the following statement is true about the van der Waals equation? Very, very good. True. Now, recall, we said ideal gas and real gas. Now, the fact remains that if you can recall what we learned in earlier on last class, that PV is equals to nRC. Now, there were some corrections to that. And some of the corrections was in two forms. And that correction was what led to what they call van der Waals equation of state. What was the correction? The correction was now, recall I said earlier on, that under the assumptions that gases do not exert either attractive or repulsive force. But in van der Waals equation of state, we have to what? Account for it. We have to account for the fact that there will be attractive or repulsive force between the gas molecules. That's what van der Waals was trying to do. So when he did that, he had to what? Correct the pressure. And how did he correct the pressure? He corrected the pressure by using what? A. So A is the correction for the intermolecular force present in the what? In the gas molecules. So the A was corrected. And what did he do to that? What did he do? He corrected pressure. The next he corrected was what? Was volume. And how did he correct volume? He accounted for the fact that we said that the volume of the gas is negligible. But our one said, no, it is not negligible. We have to account for it. And how do you account for it? They accounted for it by what? By B. So B is the correction for the volume. So B is the correction for the volume of the gas. B is the correction for the volume of the gas. Now, you said all this earlier on. Now, what were the terms that were used to correct it? Let's discuss about that quickly. Because for a while, he modified the equation. He modified it. So let's see how he modified it. Let's see it quickly. So what he did was that for this, he did P plus AN square over V square. V minus NB is equals to nRC. So this accounted for the volume change. This accounted for the what? For the pressure. I did that again. You know, we said that the pressure is not either attractive or repulsive force. So this is correcting it. And what is the term that's correcting it is what? Is EN square over B square. What is correcting the volume here? NB. So we now look at the question there and understand what it wants us to do. Now, from the question there, if you can read the question very well, fine, we know the equation of state, or we know the van der Waals equation of state as P plus AN square over V square, V plus NB is equals to nRT. Then, if you look at the question there, it said the major pressure decreased by this, decreased by, we now ask ourselves, because what does it mean? Fine, this corrected it. Is it increasing? Is it what? Decreasing? Then we'll look at the options and try to pick which of them works well for it. Now, from this, let's say for example now, if the pressure is 5 atm, How will this affect the pressure under van der Waals? Look at the options there. Look at the options there. They said the major volume increase. They said each of the following statement is true about the van der Waals equation of state. So look at this V minus NB. We know that earlier on we look at the option. Option B is wrong, totally wrong. The major pressure decreases by the term N square A over V. That is wrong. The major pressure actually increases by that term. You can see it's a plus now. It increases. So that means if I have 5 HCM, no matter let's say the pressure, let's say for in the normal region of PV continentality, if pressure is 5 HCM, that means the pressure will increase. Why? Because I'm adding AN square over B square. No matter the value, it will increase. It will increase. Even though A is 2, N is, let's say A is 0.05, N is 1, V is maybe 0.5. No matter, even though it's even a 0.1 or 0.2 increase, it's still an increase. So the measured pressure will always increase. But the question is now, what factor will it increase? It will increase by a factor of AN square over B square. So that option A would have been correct if it had increased, but it said decrease. No. So option A and option B goes away. Then we go to V minus NB. It said the measured volume, does it increase or decrease? From here, you can clearly say that it will decrease by a factor of what? Of N. Increase. So it will decrease rather. So the answer for that question is the measured volume decreases by the term NB. The measured volume decreases by the term M. No matter how, if let's say you get 20 mil, you have to subtract NB from it. Even though let's say B is 0.5, N is 1, you are still subtracting it from the 20 mil. So that answers that question. So please note this thing. Very good example, very good question. And this question is from this thing. It's from 2021 JUPEB. That year they treated, there were a lot of questions from this part in that year. In that under 20, a lot of questions, very, very good questions. So please, I advise everybody to please try to practice more questions. Now, next question there. They said equal volume of all gases at the same temperature and pressure contain equal number of molecules. The statement of what? What statement is that? Avogadro's law. Equal volume of all gases at the same temperature and pressure contain the same equal number of moles. Equal number of moles. Very, very popular. Very, very popular in secondary school. If you call it KN. So you can say V1 over N1 is equals to V2 over N. Very popular thing in secondary school. So we don't joke with things like that here. We don't joke with things like that here. Please pay attention, like I said. So V1 over N1 is equal to V2 over N2 under that is Avogadro's law. Now, the total pressure of a mixture of gas is equal to the sum of the partial pressure of all the gas reactant. That is very correct. That is what Dalton's law, partial pressure. Dalton's law. And in that way, that means if I say I have A, B, C present in a gas chamber, that means PA, partial pressure of A, plus partial pressure of B, plus partial pressure of C will be equal to the total pressure. Total pressure. Very good question. Very good question. The next question, the real gases show nearly ideal behavior at, you've done it before. So it showed nearly ideal behavior at what? Low pressure and high temperature. We did that earlier today. You know, the gases, you have the highest rate of diversion. I didn't talk about it last class and I decided to quickly put it back. Now, let's consider gases together in a room. Which of them will diffuse faster in a room? How do we know that? We discussed something again that we talked about last class. And what was that? That the rate of diffusion of a gas is inversely proportional to the square root of the vapor density. In this, the vapor density can also be what? Can also be molecular mass or molecular mass. That means that rate will increase if molecular mass should what? Decrease. That means we expect gases of lower molecular weight should diffuse what? At a faster rate. So when you see such question, please pick the gas with the what? Lowest molecular weight. Lowest molecular weight. So we did the question. CH4 is 16, NH3 is 17, N2 is 28, CO2 is 44. So we can go with what? CH4. Why? Because it is what? 16 gram per mole. That is the molecular weight. So it will diffuse faster. It has the highest rate. The compensatory factor Z, that is the extent to which a real gas deviates from ideal behavior, is given by, how do we measure? Now, we said earlier on that ideal gas can deviate to real gas. Now, the measurement of it is what they call compressibility factor. Compressibility factor. Compressibility factor. Compressibility factor. Compressibility factor. Let's quickly look at something. Let's quickly look at something. Look at something. Compressibility factor. Now, in compressibility factor, we said Z is equals to P over what? RT. PV over RT. PV over RT. This is what you need to know under compressibility factor. So this is the measurement of ideal gas and real gas. Now, we are going to your actual question. This is a very good question. 2021. See that in 2021 again. Write the Van der Waals equation and state all the parameters. That's the question. Dot the equation and write the parameters and tell us the parameters. You get your full answer. Let's recall the formula: P plus AN square over V square. V minus NB is equals to nRT. What is P? P is pressure. P is pressure. What is A? A is the correction of the intermolecular forces between the molecules of gas. I take that again. That A is the correction of the magnitude of the intermolecular forces of attraction present in the molecule. What is N? Number of moles. V, volume. V again, volume. N, number of moles. Why B? B is the correction of the magnitude of the negligible volume. That is, the correction is B. N again is number of moles. R is gas constant. And T is what? Temperature. Temperature. Very good. I get your full marks. Get your full marks. Now, next question there is still under it. We are still under it. That if sulfur 4 oxide were an ideal gas, the pressure at 0 degrees Celsius, temperature is what? 0 degrees Celsius. Please, when you see that, is convert. How do you convert from temperature to, how do you convert from Celsius to Kelvin? You add 273 degrees Celsius, degree Kelvin. What do you do? This like you saying 273 Kelvin. Number of mole is 1 mole. Occupying volume is 22.4 liters. Would be 1 atm. Pressure is equal to 1 atm. Use the Van der Waals equation to estimate the pressure of the volume. To estimate the pressure of the volume of 1 mole of SO2 at 0 degrees Celsius. And we are giving A. A is equals to 6.865 liters square atm per mole. And B is equals to 0.05679 liter per mole. Please, I wrote out this unit. Please, you can even be asked units in the exam. So please note the unit of A and B. Please note the unit. So we are now, this is the pressure at ideal gas region. We now want to solve for the pressure in real gas region. That is Van der Waals. So how can we do that? Are we giving the volume? Yes, we are giving the volume. Are we giving A and B? Yes. Are we giving N? Yes. Temperature? Yes. R? Yes. What will be the R? We look at the pressure. Pressure is in, so the pressure, don't get your pressure in atm, and your volume is in liters already. What R do you use? Please and please use 0.0821 atm dm cube per mole per Kelvin. Now we can what? What can we do? We can easily perform some little, not a little magic, and just so from here, pressure is the pressure is the unknown. I can quickly do something. So P will be equals to, or better say P plus, what is AN square? 6.865 times N is 1, volume is 22.4, all square is equals to, what is your nRT? nRT, N is 1, R is 0.0821, and temperature is 273 divided by V minus ND. V is 22.4 minus 0.05679. Now let's solve this together. So please, in this part, we don't use to always rush. We take our time. We always take our time to do things like this. We take our time. You don't make funny mistake. Funny mistake. So please pay attention. So I have my calculator here. So I can easily solve. So let's do this. So this will be P plus 6.865 divided by it's like you're saying 6.865 over 501.76. 501.76 equals to 32.4 minus 0.05679. That's like you say 22.34321. So because of accuracy, I taught accuracy before. So because of accuracy, I don't approximate anyhow. So I get my final answer. It's my final answer that I used to approximate very well. So I'm having 1.003137. So this is like you saying 6.865 divided by 501.76. This is P plus 0.013682 equal to 1.003137. So P is equals to 1.003137 minus 0.01368. 1.003137 minus 0.01368. The answer is 0.98945. That is the final answer. More like you saying one. Like you saying one. So that is the final answer. That is the final answer. So the next question, which is the last question, we want to solve using recalling the mole fraction. We want to solve recalling the mole fraction. Now, let's quickly do something. Now, so think of ethanol. You have ethanol and methanol. Ethanol and methanol. Met. Now, we're given the mass, we're given the vapor pressure. Depends on they calculate the mole fraction. Now, pressure is a pressure of total pressure is equals to pressure of A plus partial pressure of B. So what is the partial pressure of A? The partial pressure is like more like a sign of this. It's not up with that sign. It's equals to the mole fraction of A times the total pressure. Now, you need to get the mole fraction. What is the mole fraction of ethanol? The mole fraction of ethanol is equals to the number of moles of ethanol divided by the number of moles of ethanol plus the number of moles of methanol. So we need to do this mathematics. We need to do this mathematics. So from ethanol is C2H5OH. Ethanol is C2H5OH. So 12 times 2 is 24, plus 5 is 29, plus 1 is 30 plus 16 is 46. So we need to get the number of moles of ethanol. The moles of ethanol is equal to the mass over the molar mass. And what is the mass of ethanol? From the question there, the mass is 70 over 46. The number of moles of methanol, let's quickly do that too. Number of moles of methanol will be the mass. What is the mass of methanol? That is 30. What is the mass of methanol? Methanol is CH3OH. That is 12 plus 3 is 15, plus 1 is 16. 16 plus 16 is what? 32. So 30 over 32. 30 divided by 32. This is 0.9375 mole. Why this is 70 divided by 46? 1.5217 mole. Now this number of moles, you can also for the mole fraction of ethanol. So I want to do half. I want you guys to do the remaining yourself. So I will do for ethanol. I want you guys to do for methanol. Now, X of ethanol because number of moles of ethanol is 1.5217 divided by 0.9375 plus 1.5217. So 0.9375 plus 1.5217. We are divided by 2.4592, 1.5217. So 1.5217 divided by 2.4592. That is 0.662. Now, somebody that is, you are working with time, so you need to be very, very smart. So what do you do is now, let's say for example, I have limited amount of time now, currently now, for me to get the X of methanol. Why go through this long process again? I can easily do. Recall that X ethanol plus X methanol must always give you 1. The movement of everything, if you have A and B and C, movement of A, movement of B, and movement of C must always sum up to give you 1. So why waste your time? X methanol now will be equals to 1 minus X ethanol. And that is 1 minus 0.62. And that is 0.38. If you try it, you get the same answer. You get the same answer. And C, it said calculate pressure of each component and total vapor pressure of the solution. Very nice question. We are still working under Dalton's law. You see Dalton's law? It can really take us to a place that we need to understand. So we were told earlier on that the vapor pressure of ethanol is this, and methanol is this. So now to calculate the pressure of each component and total vapor pressure of the solution. We know that since we said that the total vapor pressure of the solution will be the partial pressure of A plus the partial pressure of what? B. Let's get the partial pressure of ethanol first. That will be equal to X of ethanol times pressure, total pressure there. What is X of ethanol? X of ethanol, like we did, is what? 0.62 times what is the pressure of ethanol? The pressure of ethanol is 75 millimeter mercury. 75. That is like you saying 0.62 times 75, and that is 46.5 millimeter mercury. So guys, we can attempt the partial pressure for methanol, and when we do that, you can easily sum them up to get the pressure of the solution. The pressure of the solution will be equal to pressure of ethanol plus the pressure of methanol. And with this, we say we can close kinetic molecular theory of gases too, and I will be dropping practice questions for everybody to solve one way or the other, and we'll look for ways in which we can also try to drop answers before that time. So guys, thanks for your time. I have questions. I think we have a few minutes, just 2 minutes. Let's drop questions, please. Let's not drop questions. Let's see if we can easily attempt them quickly. Thanks for your time, guys. We'll be waiting.